So, welcome back from. So yesterday's last lecture was yesterday, and we started looking at symmetries of the positive cone. And basically, there were two types of symmetries. So let's just. Is probably wrong. 4. And there were two types that we looked at. So one would be a function of this form. We've looked at several times that we emphasized that this is a positive map. Now here is S is just any invertible map. And I write also linear, or we could have phi of x, S star, x star, S, where S is invertible, and conjugate linear. So in each case, the invertibility guarantees that you can invert the map phi. So phi is also invertible. Is then order isomorphism. Which means that not only is it positive, but it's also, we have the inverse conclusion, which of course I can get by using the positivity of the inverse. So an image is positive if and only if the element is positive. Right? Okay, so now there is an obvious question that what other order isomorphisms are there? And so today we'll look at the theorem that says all order isomorphisms C of H are of this form. Or of one of these two forms, actually. Right? Okay, so there is a variant of this. So if we conjugate with this with S star S like that, then this does not necessarily satisfy our definition of a channel. Namely, part of the definition of a channel was that the identity goes to the identity in the Heisenberg picture, or in the Schrödinger picture that is trace preserving. So probability is preserved, and these maps here, they sort of map the cone around, but have no special relation to the normalization condition. So actually there is a normalized version of this. So another theorem. So let me state that in the Schrödinger picture. So let phi, and I put a star down there to make the connection to this thing. Phi star is now a linear operator. And we want to characterize equivalence of this order isomorphism condition. So this is a linear map, and assume either. So they're actually different kinds of conditions. So one possibility is to say that that phi star maps pure states to pure states. And here we need a little extra condition, because there is a trivial way to map all states to pure states, namely map everything onto the same pure state. So we have to assume also that is and is not constant on states. So it's not that everything is mapped to the same pure state. Right? There's no assumption here on the inverse, actually. Right? So I'm not assuming that we actually have an inverse, but this is, of course, part of the second version. So all phi star maps states to states and is invertible with the same property. Or its inverse has the same property. So the inverse exists and it has the same property. So this is basically saying that we have an order isomorphism. And if we think of the positive cone on the trace class to be given by just the multiples of the states, right? Then it's clear that how this translates. And the conclusion of this theorem would be then phi star of rho is S rho S star, which is just the adjoint of the other guys, right? On phi star rho is S rho star S linear S conjugate linear. With S either unitary or conjugate unitary. And of course, there's a the unitarity is what we get as an extra condition to make the normalization right. Right? Okay, so I'm actually not going to prove the whole thing, but just give you some of the basic arguments. Okay, so let's let's say proof sketches. I didn't. One thing that I wanted to note is that this theorem with the first kind of premise is actually known as Wigner's theorem. Right? So this is either one. This is pretty much the condition that Wigner imposed. Right? And that's a famous standard result in quantum mechanics, depending on what kind of course you got. If you have it from somebody slightly mathematically minded, it would probably have been mentioned in your course. Right? But actually, who heard about Wigner's theorem before in the quantum mechanics lecture? Okay, so it's not so bad. Huh? Okay, so now first. So there are two versions here. There is the normalized and the unnormalized version. So how are they connected? Right? So reducing unnormalized to normalized. So that is the first theorem that I wrote. How does this actually follow from Wigner's theorem? And that's very simple. So actually, phi of 1 So you're assuming now, of course, that phi is an order isomorphism. Right? And then phi of 1 has to be strictly positive. Actually I should, yeah, okay. That is, phi of 1 is larger than a constant times the identity. If that is not the case, well, okay, so I should say that I'm assuming here that we are finite dimensional. The statements as written are true also in infinite dimension. And okay, so why is that the case? Now, if suppose that you would find this were not the case, then there would be projections that vanish on the whole range of phi, because so then it would follow that there exists a projection such that P phi of A is 0 for all A. Right? So this would actually mean, why is that the case? Well, the projection would be the null projection, the eigen projection of eigenvalue 0 for this guy. And because A is less than a multiple of the identity, we also have so actually so P is actually the projection onto the kernel of phi of 1, and then we would always have that P phi of A. P, so for A positive, then this would be less than the norm of A times P phi of identity, P, but this is the projection onto the null space of this operator, so this would be 0. So for all positive operators we would get this. So then in particular because every, so that this implies, because this has a square root, this implies that P times phi of A has to be identically 0 for positive operators, but then you extend by linearity and get that it has to be 0 altogether. Right? So if you map on something of less, so this would mean that phi of B of H, this amounts to many linear conditions. Right? Linear conditions would fit into B of 1 minus PH, right? Which has smaller dimension, so it cannot be inverted. Right? So this shows that the null space of this operator has to be empty. Right? There could be no 0 eigenvalues here if you really have an order isomorphism. So we have so phi of 1 is actually an invertible operator. It's positive, so it follows that there exists an operator, call it S, for lack of maybe R. So that phi of 1 is equal R to the minus 2. Right? It's invertible, so, and then we can take a square root on top of that. So that's this guy. And I now define phi triple of x to be R the star is actually superfluous, right? And you can even take it positive. It doesn't really matter very much. But this map now satisfies that phi trill of 1 is equal to, well, r times r minus 2 times r, which is 1. Right? So now we've normalized it. So if you want to normalize a map, in the classical case, we just multiply with something positive that sort of corrects the normalization. Here you have to be careful to do it in a positive way, right? So that the modified map is still completely positive, still positive, right? No complete at the moment. So that's how to do that. And now if we then conclude that from the normalized version of the theorem, then if we from there we conclude that this is of the form SR, conjugation with S, then we just multiply the R on top of that and get a version, get the corresponding representation for the unnormalized case. So it's really the same theorem. There's a question?
The blackboard, the down blackboard up, please. So that I can.
You want to read this?
Yes.
Is that good enough?
Maybe lower the. Yes.
Okay, so that's. Well, okay, yeah, you're right. It's better to. This way. Okay, so this is one bit. Then we would like to have the reduction. So reducing. So let's say condition 1 actually follows from 2, right? So now suppose we have an order isomorphism that is normalized. So then it's clear that which is actually equivalent to saying that phi is an order isomorphism, just by taking adjoints. And so from that we would like to conclude Wigner's assumption. But we already, it's clear that two states get mapped to states. Now, why do pure states have to go to pure states? Well, this is obvious for an order isomorphism, right? So purity is a condition phrased in terms of positivity. I can say what a pure state is, or let's say an extreme ray is. That's a purely ordered theoretical concept. So it automatically maps under an order isomorphism. Right? So automatically preserved by order isomorphism. This is the fast track version of this argument, right? So I'm saying it because it's good to know this, to see this kind of structure. So if we're actually talking about order isomorphisms and we're talking about notions that can be defined in terms of order, then they automatically have to transfer. So how would this look, for example? So suppose rho is extremal. We want to show that phi rho is also extremal, right? If phi is an order isomorphism, right? If Now, what is this, and how do we show this? From what I said, this should be a trivial proof that just shuffles around a few symbols. It doesn't really, there shouldn't be any work involved, right? So let's see how we can do this without doing any work. So suppose that phi of rho, to show that something is extremal, I have to do this. I have to assume that this is actually written as a convex combination of states. But then I can just take the inverse of phi. So this implies, by applying the inverse, that rho is equal to lambda phi of rho 1, phi minus 1, sorry, plus phi minus 1 of rho 2. And there you have a decomposition of rho. Now this, because rho is extremal, so here apply phi minus 1, now rho is extremal. From that you get, because rho is extremal, you get that phi minus 1 of rho 1 is equal to rho. And of course, rho I, we could say. Both of them are equal to, actually have to be equal to rho. That's the extremality condition. Now, I just apply phi again, so I get that rho I is equal to phi of rho. So our assumed decomposition of phi of rho actually has to be into identical parts. Right? So that phi of rho is also extremal. Now this sort of argument really just maps things isomorphically around, and you don't actually have to do this argument. Right? That was my point in saying this. Right? As soon as you know that extremality can be written in terms of the linear structure and the positivity, then this is obvious. Right? So now, basically for the whole thing now, it remains to prove Wigner's theorem. So it remains to prove Wigner's theorem. And this I'm not going to do, because you know it already, right? So, okay, that's cheating. So the typical proofs that are around aren't, they take some work, right? It's not a trivial statement at all. So I'll do the next best thing and explain how it would work in the simplest case, and then leave it to you to maybe look it up in full glory. Right? So we'll not do this. Unless you tell me after the argument that I give that you really would want to see the full thing, then I have to prepare that a little bit and tell you next time. Right? But look at qubits. So we'll basically prove it for qubits. Now, what is the statement actually? So maybe I should erase it a little bit, leaving the theorem up. Okay, these three can go. So the next coming up is the proof of Wigner's theorem for qubits. Okay, so of course the thing to look at here is the Bloch sphere. Huh? So we have the Bloch sphere representation. And now remember where the Bloch sphere lives, what the kind of geometric object it is. We are expanding Hermitian elements in real coordinates. So rho in here would be 1/2 the identity. Plus some Ri sigma I, right? And Ri would be, now these are R is in R3, the vector is in R3, and the absolute value is less than 1. So this is what we know about the state space. Now if we have a map, if we look at phi of rho, first of all, this is supposed to be a linear map, and it also maps the normalized things into normalized things. So it has the same sort of expansion. Right? So this has to be 1/2 identity plus, and now some, let's call this R prime in sigma. Right? So that's the same notation. Wait a minute, that 1/2 should go outside, so that the absolute value of R is actually 1 and not 1/2. Right? So, but it has the same sort of representation. And the map that maps this vector to R prime must be a linear map, because phi is linear. Right? Must be linear. So let's give a name to that map. It should be something related to phi. I don't know. So call this R prime. Call this, just to make clear that this is basically the same as the map phi. So phi twiddle is a linear map from R3 to R3. Right? So what else do we know? We know that the Bloch sphere is mapped to itself. What does that mean? Well, Euclidean distance for this map doesn't increase, right? So it's a contraction. But we also know that the map is onto the unit sphere, because we can invert. If we have a positive inverse, it has the same property, right? So it doesn't increase the norm, but it can also not decrease it, because we have an inverse. Right? So we know that the absolute value of phi twiddle of R, this is the Euclidean absolute value, right, is the same as the absolute value of R. Right? And here this is Euclidean norm. Just the ordinary length of vectors. So what maps have this property? So it follows that phi twiddle is orthogonal. That's basically orthogonal now. This is the definition of an orthogonal map. So you could say that phi twiddle transpose times phi twiddle is the identity. Right? That's another way to define it. But that's just saying that the scalar product is preserved. Now if the norm is preserved, the scalar product is also preserved, because you can extract the scalar product by polarization from the norm. So this is Okay. So it's an orthogonal map. Now they come in two kinds. And this is why I'm coming up with this example, to make clear how the geometry of linear and antilinear things actually appear in this qubit case of Wigner's theorem. Right? So either phi twiddle, so the determinant of this guy is first of all real, because it's a map on R3, so the matrix elements are real. So we have an explicit formula for the determinant in terms of the matrix elements, and therefore this is a real number. And from this equation, you see that this number has to have absolute value 1. Right? Now there are only two ways, right? So this has to be plus minus 1. And that's an interesting distinction. Right? This is actually the core of the distinction for unitary versus anti-unitary. So let's have a look at that. So two cases to look at. One is the determinant of phi twiddle is plus 1. Then we know what this is. This is actually a rotation. So this is a rotation. So you can easily check that phi of rho is u rho u star for some u. If you make a rotation in SU2, that is, you take an arbitrary unitary operator, we can take it to have determinant 1. Right? Then what does it implement? It will also make such a map. And you just go through your table and see that you can make a rotation around any axis by choosing u properly. Right? Basically, you choose, if you want a rotation around a particular axis, you take the angular momentum vector in that direction. I'm talking to physicists here, so I can say things like that. Right? So the 1/2, the Pauli matrices are the angular momentum components, and then I exponentiate, and then I get something that does the rotation around that axis. So the Hamiltonian for that one parameter group of rotations will be proportional to the axis direction. That will therefore be invariant, and therefore also in the Bloch sphere, this will be the invariant direction. Right? And then you just see that you get all angles. Right? So all rotations can be built by unitary operators. Okay, so there's a second case. So if determinant of phi twiddle is -1, then it's enough to write this as a product of two order isomorphisms. One of them is maybe a standard type that we know, and the other factor would then be a unitary one, but we know all those. Right? So the other would have determinant 1, and we know those are unitary. Corresponds exactly to saying that a general anti-unitary operator is split into a sum of a particular one and an arbitrary unitary rotation. Right? So we know a prototype. Which is phi twiddle is the following matrix. That's an orthogonal matrix with determinant -1. It flips the -1 direction. Now, if you think of an expansion in terms of Pauli operators, Pauli 1 is just ones on the off diagonal. Pauli 3 is just 1 - 1. They are real, right? So they don't, and they are also equal to their own transposes, right? So these are operators that are invariant in the transpose, but under transpose the two direction will change, because Pauli 2, remember, sigma 2 is -IR. So this would change under transposition. would change sign and the transposition. So if you apply that to a linear combination like that, you see that what you actually get is a reflection of the two direction. Right? So the sign of the two component, the two component conventionally this direction, if you look at me, then, so that would be the standard reflection. Now, all others with, let's say phi twiddle naught or something like that. So all others with det -1 can be written as phi twiddle 0 times phi twiddle 0 phi twiddle, right? And now this will have determinant 1. This has so the determinant is neatly split off. Right? So this has determinant +1. So this corresponds exactly to this. This is implemented by the complex conjugation. We've checked that last time, right? So so it's a complex conjugation followed with a unitary, which is just the arbitrary thing that you can implement with an anti-unitary. Follows this anti-unitary. So, okay, so Wigner's theorem for qubits says that we have directly translates into a dichotomy for orthogonal transformations in R3, something that we are very much familiar with. They come in two kinds, and they're separated by the determinant, which then actually gives precisely the distinction between the unitarily and the anti-unitarily implemented symmetries of the Bloch sphere. And so this is Wigner's. This is exactly the dichotomy of Wigner. Okay, let me see what I had planned. Yeah, so one general remark on all this. So this is all I wanted to say about the proof. Of course, the general proof might start from there, and you could sort of piece it together by unitarily implemented things on two-dimensional subspaces. That's not necessarily the most elegant way to do it. Right? So, but you can imagine how it would roughly work. Okay, so but take Wigner's theorem as a fact now. One general remark that we have to make. So always S is defined by the order isomorphism, right? Up to a phase. Indeed, if you multiply the S with a phase, then clearly we have an S star and an S, and so the phases just drop out. Right? So, but this is the only non-uniqueness. So if I try to implement the same phi with different operators S, well, take the one for the inverse for one of the two versions, and then the product would have to implement the identity transformation. Now, the only operators that implement the identity transformation, they would have to be operators that commute with everything, right? If S star rho S is equal to rho for all rho, that just means if I multiply with S star from the side, that it commutes with everything. Now, operators that commute with all other operators have to be multiples of the identity, and therefore this free phase that you get that you can see by inspection, right? This is clearly the kind of non-uniqueness that you have, is really also all the non-uniqueness. Right? Okay, so So let us look at a few more symmetries, and actually symmetry groups. So this remark that the operator that implements a symmetry is only defined up to a phase is very important if you want to look at groups, because then you have to work with these phases, right? So let us make a few examples of symmetry groups. Examples. So the first example is you want a group of symmetries that is as small as possible, apart from the trivial one. It has just one other element. Right? So a two-element group, there the element that is not equal to the identity has to square to the identity. Right? So the group is has the identity and an involution. Right? So that means that if I take the order isomorphism and apply it twice, I have to get back x. Right? So this implies that if I do this with an S, maybe with a unitary or anti-unitary kind, then S squared would actually implement this operator. But we don't really know, so S squared has to be a multiple of the identity, right? So that's into the I alpha times the unit operator. I'm consistently now looking at the normalized case, so these will be unitary operators. And so we have unitary or anti-unitary operators with square 1. So what do they do? Right? So there is a unitary and an anti-unitary version here. So we have two cases. So first, so let's say A, the unitary case. There we can change, without changing anything, we can replace S by, minus I alpha S. So that will be an operator that implements the same symmetry, but has the additional property that S squared is now equal to 1. Right? I'm just taking out this factor out of S. And that's obvious that you get an equivalent choice of your symmetry implementing operator S, but now it actually has square 1. Now this is unitary operator, so it can have two eigenvalues. It can be diagonalized, and because of this equation, S squared is equal to the identity, the same equation has to hold for the eigenvalues, right? So the eigenvalues actually, they have to be on the unit circle, so, well, you don't even have to say that. It's clear that S has eigenvalues plus minus 1. If you think of it in terms of real, in three-dimensional geometry, the eigenvalues of a reflection operator are the directions that it will invert. Right? So some directions get inverted, others stay the same. And this distinction is just done by the eigenspaces, so you could say that S is equal to 2p minus 1, where p is a projection onto the plus 1 eigenspace. So specifying such unitary operators is the same as defining a subspace on which the S is just constant, just the identity, and another subspace on which it just inverts the sign. Right? And okay, so this is kind of simple. And the unitary inversions of the Bloch sphere, the reflections of the Bloch sphere that are unitary, which one are those? Well, they have to change two signs for the phi twiddle here has to have two signs, two minus ones, right? So that the determinant is plus one. Now, this is still a rotation, namely if you fix an axis and you rotate by pi. So reflection at an axis is the same as rotating, or in 2 dimensions, a point reflection is the same as a rotation by 180 degrees. Right? So those are the ones that you get here. Determinant 1 means rotation, and indeed they are rotations, and this is the unitary, kind of unitary that you get. Now, so B is the anti-unitary case. I tried to say conjugate, but I can't. Now, then S squared is also something. Right? S squared has to be a multiple of the identity. S squared is e to the I alpha identity. That's still true. But now we can't have, the alpha is not arbitrary anymore, because if you look at S cubed, right, you just apply that 3 times, then you can either write that as e to the I alpha S, but you can also, this used to be S squared, right? But you can also write it as S times S squared, right? Which is S times e to the I alpha identity. Right? But S is conjugate unitary. So this has to be equal to e to the minus I alpha S. So that means e to the I alpha is equal to e to the minus I alpha. So it follows that alpha is 0 or 1. So either you have this, or you can say S squared is plus minus 1. So we have examples of that in the Bloch sphere as well. So the S squared, so we have two kinds of reflections. One is the transposition reflection. This was implemented by just complex conjugation. Complex conjugation squared is of course the identity, right? So this is an example where the square is 1. Now this in the Bloch sphere, this is the inversion of one direction. So you have 1 minus 1 on the diagonal and otherwise 1s, right? So S squared, so in Bloch sphere, S squared is 1 plus 1. This is like complex conjugation. And S squared is minus 1. This would be an operator with determinant so the phi twiddle has determinant minus 1, and the only other thing I can do here is just a complete inversion. That is minus phi twiddle would be minus 1. Right? So this is the inversion of Bloch sphere at the center. Right? Or also, as it's called, the universal knot. I think I mentioned that before. Okay, so this is the complete analysis of the possible symmetry representation of the simplest group ever. So let's look at the next example. There's maybe one little thing to mention here, that in the unitary case, you could change the value of S squared by putting a phase on S. In the anti-unitary case, you can't. Right? This is also kind of clear from from this little computation, but why does that not work? If you take s squared, then you would have e to the I alpha s, e to the I alpha s, right? If you try to rotate s by a phase. But the e to I alpha, which is between the two s's, comes out at the e to the minus I alpha and cancels the other one. So you cannot actually fix this factor by putting a phase on. So there's really three very different, geometrically very different kinds of involutions in quantum mechanics. Right? The unitary ones, the anti-unitary with square 1, and the anti-unitary with square minus 1. Okay, so some more things about groups. Okay, so I think we have a numbering of the examples. So second example, one parameter groups. So there you would have a family of such transformations, let's call them phi t, and has a property, so for t in R, this is the one parameter on which this depends. Right? An example will of course be the time evolution, and there you have phi t plus s is the composition of phi t and phi s. Right? So that means there are transformations form a group. And so from that you would get operators st that implement phi t, and you have that st plus s has to be a phase that depends on these values, st times ss. Right? So this is what the group relation becomes. You can never directly conclude from such an equation between the automorphisms or the order isomorphisms that the implementing unitaries also multiply like that. This is not, in general, clear. Right? So, but then let's just put that into the theorem. Alpha can be chosen trivial. So, what does it mean can be chosen? Well, for each, I can choose a phase for every st. And if I do that in a clever way, the statement is that I can actually make this vanish. Right? So that make the phase go away. So alpha can be chosen to be trivial. And well, okay. So that's the first statement. Second statement, if this function is continuous, well, it must be conditioned in terms of phi, right? Sorry. If the following kind of function, I take an expectation value of phi t of a psi, so this function is continuous for all phi psi a. Then there is generally unbounded self-adjoint operator H, so that ST is e to the minus I H T. Now, a self-adjoint operator, so far I only talked about bounded operators, always. Now, what is a self-adjoint unbounded operator? Well, it's one that can be transformed to a multiplication operator with a possibly unbounded function. And the function has to be real for the thing to be self-adjoint. And that's all. So it's sort of defined by the spectral theorem. And so this part 2 is the stone von Neumann theorem. So of course we use that in quantum mechanics all the time. Right? So if you want to make, we know that we have a time evolution, it's natural to assume that it's not wildly discontinuous, and therefore you have a Hamiltonian that will implement it. The Hamiltonian is typically unbounded, but this theorem tells you nothing about what the Hamiltonian actually is, of course. Right? There's some unbounded self-adjoint operator, but which one you choose for your hydrogen atom, that's a completely different story. Right? But you know that the form of the Schrödinger equation, I mean, if you take the derivative here, you basically get the Schrödinger equation. So the form of the Schrödinger equation is pretty much fixed by the basic structure of quantum mechanics, but, well, which operator to take, that's another business. Of course, von Neumann made the spectral theorem for unbounded self-adjoint operators precisely for this purpose. Right? Okay, so let us go on with the examples here. Other groups. Right? So you would have a map. So you would be interested in let's say other groups. Let's say G is the name of the group, and then you have a map. Phi would be a map from G to the order isomorphisms. Right? So for every G, you would have an order isomorphism phi G, and in such a way that phi G, phi H is phi GH. Right? So they multiply. This is saying that I have a group acting as symmetries of the quantum mechanical system. And so this implies there exists unitary operators, UG, so that UH is some function, some phase function mu gh. So you don't quite get what is called a representation. A representation is something of the group G. A unitary representation is one where you don't have this factor. So now you generally have this factor in quantum mechanics. And so this is called a representation up to a factor. I don't think I have to explain that terminology now. Other words for that would be ray representation. I think this is Wigner's terminology. Why that? Well, the pure states would each define a ray in Hilbert space. That is the vector plus all its complex multiples, right? And so because the complex multiples of a wave function still define the same state, so ket bra phi phi doesn't depend on a phase that I put on phi. So one way to think of this is as a map between rays. Actually, this is also Wigner's terminology for proving Wigner's theorem. Right? So this is why it's a ray representation. It's not a representation at the linear vector space level, but it is a transformation of rays. That's one way to see that. Right? And the factors would be there. Another term for the same thing is a projective representation. So this is projective as in projective geometry. Are you familiar with projective geometry at all? So actually, it's not really part of the physics curriculum. So in a projective space, you think of the points in a projective space are actually the one-dimensional subspaces of another space. So if you think of projective geometry in the sense of 3D, I mean how to put a 3D picture on paper, right? Then what you actually do is I have the origin of your space then is your eye, and you have the one-dimensional rays going away, and then you then you get an image of a picture like that, and you cut that with a plane. Right? This is how to make pictures of 3D objects. But now you can tilt the plane and move it around. What remains part of the geometry is this notion of rays. Right? So the points, in that sense, the points of a projective geometry are rays in a space, and actually if the line that you're looking at in your, let's say, 3D space, if you think of optics, if that is parallel to your plane on which you represent the picture, then it will go off to infinity. Right? So there are infinite points automatically there also. And but again, the same motif, points are actually rays. So this is why people call that a projective representation. Okay, so can we choose the factor to be trivial always? Huh? So the factor omega cannot always be chosen trivial. There is a way to go back to a representation. So if you look up a mathematics book on representation theory, you get a lot of representation theory, but usually only a small chapter on projective representations. So actually the theory, things like Schur's lemma, I'll mention that briefly in a little while. So some of the useful tools of representation theory are available for representations, but not for projective representations. So actually there is a way to, that can still work with proper representations. Those are the ones where I don't have to add such a qualifier. That means omega is 1. Right? by including the phase factors in the group. So you go to another group, let's say G twiddle. This is a so-called central extension. G. And this is basically just G cross S, where this is the set of phases. So S here stands for circle, the unit circle in the complex plane, right? And so right, we have to define a multiplication law for this group, and we have to define a multiplication law for this group, and we do this in such a way that this is just this factor up there, right? So so actually, if we compose G and some phase, I have to find it. Let's say psi is a phase. Right? So this means that psi is a complex number, and the absolute value of psi is 1. Right? So let's say G1 psi 1, G2 psi 2. This is equal to, well, you just multiply the group elements. You also multiply the phases, but you also put the factor in there. And then you check that the basic conditions tell you that if you have a projective representation, you actually have a representation of this group. And then you have different choices, so the factor gets into the definition of the central extension. So in this way you can reduce the projective representation theory to the ordinary representation theory. So I won't go into this in much detail, right, because it's a bit besides our main line. But the standard example of this, so that's 2, 3, 4. Take the group to be SU2. So, sorry. Take the group to be SO3. So the rotations. This is of course physically extremely important, because of course rotations play a big role in physics. But so if we make a representation of this now. This will generally projective representation, and so one representation here is to say that, projective representation on a qubit, that is, the Hilbert space is just C2, right? Okay, so how do we do that? SO3 are the rotations. So I look at a generator, at a one-dimensional subgroup of this, let's say, okay, so one rotation here by around an axis, let's say this is the axis, this is the angle. You could write as the exponential, matrix exponential of alpha times an antisymmetric matrix which would have 1, 2, 3 minus E2, E1 minus E1, E2 minus E3, something like that. Right? So you build a matrix, antisymmetric matrix out of that, and so this gives you a general rotation. This is just a rotation around so you could write this as the exponential of alpha times a vector of operators that you build like that, scalar product with a direction, and then so U of the same kind of rotation. This now should be a 2 by 2 matrix, and you do the same thing. You take the exponential of I alpha Pauli vector in E and divide by 2. So, which is to say that you could think of this as the angular momentum operators in 3 dimensions. They are the generators of the rotations, and here we have the sigma over 2 would be the generators for the rotations in SU2. Right? So this is a spin 1/2 system, and that's the way you get it. Okay, so my main point here is that you, around any axis, but a rotation around 2 pi, if you write it like that, is going to be -1. Right? If you then you would have e to the I pi sigma in E. Well, take the unit vector in the 3 direction. So it's e to the I pi sigma 3. Sigma 3 has just 2 signs, but e to the plus I pi and to the minus I pi are both just -1. Right? So you get the -1 operator. That will be true in every direction. This is, in one sense, this is bad because obviously the rotation around any axis by 2 pi is the identity. So your representation is not a representation, but a projective representation. You have a factor -1 here. And the same kind of ambiguity is, of course, present all over the group. So this is an example where you cannot get rid of the factor. There's no way to choose phases for your rotation operators so that this phenomenon vanishes. Okay, so this is one remark about the projective representations, and this will be true for any half-integer spin representation. Now, so I wonder how much I should say about this. So who knows what an irreducible representation is, and is familiar with Schur's lemma and all that stuff? So I'll just make a few remarks and reminders here. So the notion of irreducible representation is a way to reduce a complex, a general representation to some simpler cases, namely these building blocks that are called irreducible representations. And the definition is that if you have any operator that commutes with all these, then it follows that X is a multiple of the identity. Right? So that's a definition of an irreducible representation. And so the idea of analyzing a difficult representation into so try to general representation, try to decompose. So you have, like, let's say, the first irreducible, different irreducible representations. I think I'll have to do this in more detail sometime later. But this would be a Bloch diagonal form, so that on each of these subspaces belonging to this Bloch decompositions, you have an irreducible representation. And now I just want to make a brief remark about that. So for SL3, which is, so this covering, universal covering group there is SU2, so actually every projective representation of SO3 actually becomes a proper representation of SU2. So these are parameterized by S. And S takes value 0, 1, half, 1, and so on. And they have dimensions 2s plus 1, which then runs from, 1, 2, 3, and so on. So here the odd dimensions belong to integer spin, and the even dimensions to half integer spin. And can be realized as U tensor U tensor 2s. So that this is would be, so 2s is always an integer. So this is U tensor U tensor U. Where U is now an SU2. So you get a representation of the SU2 group by taking a tensor product of 2s factors and restrict to the symmetric subspace. So of course this big tensor representation is not irreducible, but if you restrict it to the space of vectors that are to the Bose subspace. If you restrict it to that, then you get an irreducible representation again, and you can count the dimension of the symmetric subspace, and you'll find that it will just give this result. So this is a way to get all the higher spin representation in some sense painless way. And I'm mentioning this. I mean, I'm completely aware that this is a bit of a sidetrack in my main course, but I want to make the connection to these anti-unitary symmetries. That's why I'm mentioning it like that. So SU2 allows one anti-unitary, call it theta, right? That's whatever, with theta, U is U theta for all U in SU2, right? So this would be an anti-unitary operator that commutes with a representation. Now this must be unique, right? And actually if it were a linear operator, not an antilinear operator, it would have to be just a multiple of the identity. Right? But for an anti-unitary operator that doesn't work, right? This irreducibility definition has nothing to say about anti-unitary operators. So we actually find an anti-unitary operator, and we've already encountered that one, of course, which is the universal not. This is the unitary operator that implements the universal not, which is just saying that there is a symmetry for the rotation group, that is allowed here for the Bloch sphere, which is the inversion of the Bloch sphere. That clearly commutes with all the rotation. It's the operator -1 on R3. Right? So R3 in the Bloch coordinates, in that representation, it's -1, minus the identity, and of course this commutes with all the rotations. Right? So it's clear from that point of view that we should have this. The universal knot should be an operator with this property. Right? And this clearly has theta squared equal -1. We've checked that before. So this implies that the spin S representation has a unique theta something like, so that let's say commuting. Let's say the spin S version. Namely, we simply take theta tensor to S, restricted so we just tensor 2S copies of this operator, just as many copies as we have of the unitary that we want to represent. And clearly they still have to commute. Now there's a tricky thing here, which is the tensor product of anti-unitary operator or anti-linear operators. There's the only really tricky thing here is though that if you cannot tensor an anti-unitary operator, anti-linear operator with a linear operator. Why? Because it's part of the laws of tensor products that if you have a factor so if you had phi tensor psi and you replace phi by a factor times phi, you pull out this factor linearly. Now, but you could also just shove it to psi. That's still the same vector. Now, if you try to tensor a unitary and an anti-unitary operator, this would become ambiguous because on one way of reading it, you would pull it out as a factor, and on the other way of reading it, you would pull it out as a complex conjugate. So this is inconsistent, right? So you cannot make a tensor product of a unitary operator and an anti-unitary operator, but anti-unitary operators among themselves are fine. And this is what I'm doing, right? S times. And then, of course, just the commutation relation goes through. This commutes with everything. And it actually has, so this operator, let's call this theta S or something. Then we also can compute theta S squared. Well, you square all these operators. You have a -1. So this is equal to -1 to the power 2s times the identity. So that means that integer representations, so S is even, S is integer, then 2S is even, and this squares to 1. That is, if you have an integer spin representation, it commutes with a suitable anti-unitary operator, this particular anti-unitary operator, with square 1. That means that you can split your Hilbert space into a real and an imaginary part in a consistent way. So you can choose your representation matrices real. This will happen in odd dimensions, and 2s plus 1 is then odd. So in 3 dimensions, our ordinary rotation group, right, is the spin 1 representation. There we can choose the matrices real. And this will be true for all odd dimensional representations, that is integer spin. Right? Actually, this operator with this property that it commutes with that representation, as I argued before, is unique. Right? So it's either you find an anti-unitary, commuting anti-unitary that squares to 1 or to -1. This number is part of the description of the representation. Right? sort of built into the structure of the representation. And the other ones will always have this property that actually you can also see the representing the representative of the rotation by 2 pi is -1 is the same thing, right? So this is actually that's another way to memorize that. So this is the rotation around 2 pi, right? Which is represented either by -1, half integer case, or by 1 in the integer case. Okay, so I'm completely aware that this is not an introduction to the representation theory of SU2, but I assume that you know much about it. I just wanted to make the connection with these symmetries. That's why I did this, and I think that's a good point to stop. So thanks for your attention.